Okay, I hope everyone is done. Yeah, I don't know how exactly the system works, but I think it closed off for everyone. And yeah, sorry, I forgot to give you the password. Maybe next time I don't even need a password, so I didn't know how to make it a start at the same time for everyone. So I also chose the password. Now I figured out that we don't really need a password. If there is no comments, I can continue with the class. Thanks a lot for taking the quiz and hopefully you did well. So starting over, as I said, probably there is another quiz on Friday. Then next Tuesday is off, and next Friday we have the presentation for every team. That's all we have right now, and we had a successful quiz. Now let's focus on the important stuff. I can minimize this one. My sound is heard, yeah, okay. Okay, a question in chat. How much is each quiz worth? I didn't really divide it. So in total, it would be about 10 points. So very tiny. At the end, it's mostly about, like making sure you go through your notes and organize your notes on your computer so that in future you can access them and so that you browse through your notes at least one time. So, but we will mark all the teams equally. That's what I can tell you. And it's all together would be about 10 points. Now, let's continue with the course. One of the important sections or modules of the course, which is about a still design. And when you fully understand and grasp the still design concepts for earthquake, means that you are a very good structural earthquake engineer. The sources for a still design, as you already know from probably your still course, is design of steel structures, which is a CSA S16. And the latest revision that I'm aware of is from 2019, maybe edited one more time in 2021, but formally from 2019. And we are mostly focusing on chapter 27 of the code. Also, there is a handbook of steel construction with a lot of nice tables that normally accompanies the code, and it's normally very, very useful in steel design with all those nicely created tables for steel design. This design is based on limit state design, or also known as LRFD solution. No comments, nothing in chat. Yeah, an outline of what you see in class 27 of the code on seismic design, mostly divided between different types of steel structures or steel seismic resistance frames or systems with different levels of ductility. The more ductile you want, it means that you should do a better job in detailing and providing capacity protection. When you do a very good job, you get like a ductility factor of 5, say for moment resisting frames, and also a overstrength factor of 1.5, totaling to, like when multiplying them, it's 7.5. For plate valves, it goes as high as 5 multiplied by 1.6. So you can basically reduce your forces 8 times, which is, I think, a huge number. And take advantage of a good design to design for lower forces. So let's go for the scope. Clause 27 specifies the requirements for the design of members and connections in the seismic force resisting system of steel-framed building structures for the 4 seismic categories that we discussed. And the design loads are based on a ductility-related force modification factor equal to 1.5, need only satisfy the requirements of 2712. So if you are happy with 1.5, then you only need to satisfy 27.12, which is mostly probably related to the traditional or conventional type of design and construction. Some comment about truss moment resisting frame with medium ductility, and comment about the design of steel seismic force resisting systems, which are not in National Building Code of Canada, or this class 27 shall satisfy the applicable requirements of 27.1 and the provisions for a special seismic design of 2713. So if it's not particularly defined here, then we should look at 27.1 and 27.13. 13, a special seismic design. So I guess more general. However, using this one is probably easier because directly tells us what to do for all type of design. And height restrictions specified in National Building Code of Canada. We previously looked at those. Stability requirements specified in 27.1.8 and increases in factor seismic forces specified in 27.5.2, 27.6.2, and 27.12.4 may be waived, provided that the design satisfies all other requirements of Chapter 27 or Class 27. Height restrictions shall not apply in the seismic category 1 and 2 because they are like low demands. And class 27 may be applied to structures other than building structures, provided that the structure includes a clearly defined SFRS and that a level of safety and seismic performance comparable to that required by class 27 for building structures is provided. So general stuff. First, jumping into one of the last sections, the conventional construction. The system remains essentially elastic, so it's almost non-ductile throughout the earthquake. Meaning like what has been done in the past probably 100 years in a steel design. Note that ductile design has a few disadvantages, so why we always don't jump into ductile design. Normally, the more ductile structures mean they have larger displacements, and which might be an issue for non-structural components or adjacent structures. So that's also, I mean, agrees with engineering judgment. So when you make it too ductile, it moves a lot, and therefore non-structural components might be harmed or adjacent structures might be harmed. And therefore, maybe sometimes you have to take a step back and make your structure less ductile. Although you will lose on those modification factors. Another challenge is that the ductile structure may end up with a deflection limited rather than force limited design, in a way identical with the first item. Like, you design your ductile system, but then because of the limitations in deflection that you want to apply at the end, then you practically make your structure less ductile and use the advantages of ductile system. And then the top of the list, maybe, or here the bottom of the list, is that detailing ductile system is more complex, and the design of it is more complex as well, with all those capacity protection, etc. So it's a complex process, but it's kind of rewarding because it reduces the seismic load on the structure. Conventional construction may be used in seismic category 3 and 4 with height limits. For seismic category 3, it's 60 meter, and seismic category 4 is 40 meter. So if the conventional non-ductile design is used in a structure, there is a height limit for different seismic categories. Because the higher seismic categories, they see a higher earthquake demand, and therefore we cannot really go too high, too tall if the structure, if we cannot provide ductility. However, saying all that, still we will have RD 1.5 and RO 1.3, and if we multiply them, it's about 2. So still, you can reduce your forces by a factor of 2. The important discussion shows up again on capacity design, how we protect the non-ductile members. Unless otherwise specified in clause 27, seismic force assisting systems shall be designed in accordance with capacity design principles. So capacity design principle should be always in your mind, which means specific elements or mechanisms are designed and detailed to dissipate energy through yielding and nonlinear response. However, all other elements are sufficiently strong for this energy dissipation to be achieved. Like, while the intended members will yield and dissipate energy, every other member remains intact, almost intact. The structural integrity is maintained, so we don't want any collapse under vertical load. Elements and connections in the horizontal and vertical load paths are designed to resist gravity and seismic loads, obviously, and then in a way with capacity protection, because normally the connections are considered non-ductile and there should be capacity protected. Diaphragms and collector elements are capable of transferring the loads developed at each level to the seismic force assisting system. This is very important. Always think about the diaphragms and collectors that transfer the loads, and they are also capacity protected. These loads are transmitted to the foundation, and transfer of the load to foundation is, again, capacity protected. So a lot of capacity protection in order to achieve the yielding in certain members. So the factor resistance of yielding elements and mechanisms of the seismic force resisting system shall equal or exceed the maximum forces from the load combinations with seismic effects. We apply all the loads, including the seismic loads, and we design the yielding elements, the ductile elements. Then every other element should be designed for the seismic force, for the seismic load that the ductile members can take. All other elements of the seismic force resisting system, including roof and floor diaphragms, collector elements, anchorage to the foundations, and foundations shall have factored resistance equal to or greater than the forces due to gravity loads plus the lateral loads required to develop the probable resistance of all yielding elements. The lateral loads used in these calculations need not exceed those determined with RD multiplied by RO equal to 1 for foundations, anchorage to foundation, and connections that do not have a ductile governing failure mode, or RD multiplied by R0 equal to 1.3 otherwise. So basically, this is an important part. Like, you should think carefully about this. As we said, we do capacity protection, which means that we design the non-ductile members for a greater load than what we get from the, say, structural analysis. However, we don't need to go to extreme. If the upper limit for increasing the load is not having any ductility and no reduction factor. So we don't need to exceed that upper limit. Like, the upper limit for the load on non-ductile member is no reduction factor. In fact, for some members, the upper limit would be having a super small reduction factor. Therefore, yeah, so I mean, in practice, I have seen that to capacity protect certain members, you increase the load and then it skyrockets. Here it says increase the load, but there is a ceiling for that increase. So just have this paragraph in your mind. Probable yield stresses. So that's a good discussion in capacity protecting. The earthquake effects for the design of the capacity protected elements is based on the probable yield stress of the yielding elements. And the probable yielding stress is Ry Fy. The value of Ry is about 1.1, and the product Ry Fy has a minimum. For HSS, it's 460 MPa, and for other sections is 385 MPa. So here the philosophy is that there is a nominal resistance of a material, which is, say, taken as the average, maybe -1 standard deviation. So basically, assume that like the vendor has done a lot of tests and the material he is selling or they are selling has this curve. Like, some of them, like one sample shows a higher yielding, another sample shows a small yielding, and they create this curve of the variation of the yielding value with numbers, like in frequency, how many of them have certain value. And the average, which has the highest frequency, is the probable resistance. But in like our structural engineering design, we don't design for probable resistance. We are conservative and we go, say, 1 standard deviation lower to be really conservative. And then there is another reduction factor that is applied, say 90% or something. So we even go lower than that. So basically your design is based on like a structural engineering design. Typical structural engineering design is based on a value which is quite a bit lower than the probable resistance. However, that member, it's very probable, or it has 50% probability that that member really shows this much resistance, which is the probable resistance. And we want to estimate the probable resistance for capacity protection. And the best estimate is it's 10% more than the nominal resistance. Like you multiply, instead of multiplying it by 90%, as is the case for a lot of steel design, or plus minus 90%, you increase it by 10%. And there are this, you should see these two minimum values to assess the probable resistance, to back calculate in a way probable resistance of your steel member, which you use to assess the demand in capacity protection design. Materials per clause 512, the yield strength Fy used as the basis for the design shall be the specified minimum values as given in the material and product standards and specifications. Because we are relying on the material to behave in a ductile way, there are some requirements to ensure that we get what we designed for. And for grade 40.21, the minimum is 350 that we use. And similarly for ASTM A992 material, the minimum yield is 345 and the maximum is 450, which is the newest standard for W shape. And ASTM 1085, the minimum is 345 and the maximum is 485. Replace A500 for HSS. So basically, we have all these standards, and we know that we should increase the Fy by 10% and also see these minimums for the product of Ry multiplied by Fy. Probable yield stress. So for minimum yield stress, 350 or 300 or 400, the Ry that is practically used, we said that the minimum value of Ry is 1.1, but there were also minimums that we should see. And therefore, for HSS, Ry Fy is 460, and for lowest strength, and also for milder steel, Ry Fy would be 385, which is similar to what we said. Like we set a minimum of 385 and 460 for HSS. However, the Ry is at least 1.1, similarly to what we are seeing here. So just reiterating the same thing, but this is table format, so it's easier to use. Classification of sections and compactness. Wide over thickness for elements in compression is limited. And there is also section classes. The inelastic behavior of a section is based in part on the geometry of the section. The code defines 4 classes of section based on their ability to exhibit the desired inelastic behavior. So you should double check with class 11.1.1 and use the members that can go ductile. Specific clauses for specific systems will limit use of certain classes. So when you are reviewing your section 27, it tells you not to use certain classes for high ductility. Then you can go back to clause 11.1.1 and read how to classify, basically. Besides that, we have the compactness requirement, which is because under large compression load, the steel members can experience local buckling. That's to avoid the local buckling. And to reduce this risk, codes place limits of width to thickness ratios. This concept is in class 11.2. So when you are reading your section 27, just revisit class 11.1 and class 11.2 to find out about the compactness and the section class. Stability effects. Member stability effect must be considered when verifying the capacity of members subjected to combined axial load and flexure. Provisions for global stability effects, P delta, are in clause 27.1.8. Notional horizontal load must be applied in all load combinations, and applied loads are 0.5% of the total axial factor load carried by the column at the level under consideration. So in the US, we don't have it. In Canada, it's mandatory to apply the notional load to assess the basically a stability effect, and that the notional load is like 0.5% of total axial factor load, which means vertical load in your column. It's applied horizontally to push the column to the side and make sure that it's stable. It doesn't buckle. Protected zone. Another concept that you should be aware of is the concept of protected zone. That's basically the zones that a structural designer wants to yield, and he would mark it as protected on the drawing so that it's not, nobody punches a hole in those areas. In sections of a structure where inelastic deformations are expected to develop, no alterations are permitted, so no welding or connecting or punching a hole is permitted, because like a lot of this basically plastic hinge behavior is verified by tests on the full section, and any modification to the section will substantially change the behavior. Therefore, no change in those zones. The performance of these sections is typically derived from laboratory tests, so it is crucial to ensure the field condition is identical. Yeah, as I said, laboratory test has been used in verifying the behavior of like this section in bending, or when after a plastic hinge is created, and any modification will substantially change the behavior. So let's keep it the way it is. According to clause 27.1.9, the protected zone must be shown on the structural drawings and shop details. Often fabricators label them on the actual structure. So they must be shown in drawings. However, in order to avoid future changes, the fabricators also label them, so that even in long time in future, if there's a modification, nobody punches a hole or welds another system in this protected area. Yeah, let's do a few case studies or case presentations on different types of seismic force resisting systems. Steel. One of them is moderately ductile, which is MD. concentrically braced frames, like these frames are concentric, they go through one point. And it's described in clause 27.5. The reduction factor is 3 times 1.3, like about 4, which is generous. And the concentrically braced frame include tension, compression, bracing system. So one side goes into tension, the other side goes into compression. And basically this lateral load, the load path is that it goes through this member and divided between the two. One side goes into compression, this member, one side goes into tension. It's normally the chevron brace system. Tension only, chevron brace system is also covered. Tension only bracing system might also be the case, like one full member going in this direction, which takes the tension, and it's so narrow that it practically cannot take compression. So you are only dependent on the tension. Multi-tiered bracing systems, maybe you have one chevron and one tension only, that could also be. And other systems, provided that this a stable inelastic response can be demonstrated. So in these cases that you need to demonstrate something, it means that you should do detailed modeling and analysis to prove that there is a stable inelastic response. While for other cases, the code has guaranteed that in a way because of the previous analysis and test. So, I mean, mostly we prefer to use the systems that are previously verified, but if you are proposing a new system, then you need a lot of tests and analysis to prove its performance. Chevron bracing. Let's focus on the chevron bracing that is shown in the picture. Under class 27524, braces meet at the same point in the middle of the brace. So they are meeting at the midpoint of the beam. And the two of the classes there, one requires 27.5.24b, requires that both top and bottom flanges be laterally braced at the brace connection. The top and bottom flanges are braced here so that they don't buckle out. And 27524c requires that the braces be able to resist bending moments due to gravity load. So if some gravity load is transferred through these braces, which is not recommended, they should be able to resist bending moment that is caused by the gravity load. Yeah, I mean, maybe it's inevitable if you make a computer model, maybe you will see that some load is transferred here and here, some gravity load for gravity only load case. In that case, they should be able to resist bending. They shouldn't buckle because of gravity. If they buckle, they should buckle because of basically seismic force. There are two failure mode that could be imagined. Failure at the connection, like if the connection is failing in a brittle way, and failure because of buckling. If one of the members under compression buckles out in a irreversible way, and which means failure. So how do we go through the capacity design procedure for this member? Step number one, it's almost reiterating what we previously said, but more focused on this type of seismic force resisting system. First, apply the basically earthquake load and complete analysis of the structure, hand calculation, or computer model. Then you have all the design forces in all members out of analysis. However, if you remember, we previously said that for capacity protection, we only use that load in the design of the braces. And normally the compression capacity is lower, so we size the brace for compression capacity. Then, so when you are sizing the brace for compression capacity, you just use your standard solution of designing a member for compression. Even the manual of steel construction can give you, based on the member shape, say HSS, and the length, it can give you the capacity, and then you can compare with the demand and pick a proper member. Now the earthquake design maybe starts from step number 3. Now you should assess the probable capacity. Remember that you have used the reduced steel capacity for your typical conventional steel design. Now you use the increased steel capacity to determine the probable capacity. It was like at least 10% more than the yield of the, like a yield capacity of a steel should be used for probable capacity of the member. Load the frame to develop forces in brace equal to probable capacity. You can say do that by increasing this load, or maybe directly applying the brace probable capacity, and then read the forces in every other member. And then determining the load in columns, beams, and connections, and design beams, columns, and connections, which are capacity protected based on the increased load. Again, the same philosophy is used here. Brace must be the weakest link, and brace will see in elastic action. Everything else is strong and will continue to carry vertical load without any yielding. Five capacity resistance estimates. So capacity under tension, the way you learned in your steel design. Capacity under compression, similarly, or you can read it from the manual of steel construction. Probable tensile resistance is basically the same thing as a capacity under tension. However, instead of Fy, you use R times Fy, like you increase it. Probable compression resistance. Similarly, and post-buckling compression capacity, the code has a guidance for that. That's a new, maybe you haven't used a similar concept in your other design. You can estimate the post-buckling compression capacity using the code. So TR and CR, that's what you read from your manual of steel construction. Tension resistance of a member is based on the gross area. That's the easier one. There is Fy and a reduction factor, maybe 90% plus minus. Like in this case, it is 90%. And you use the whole area to assess the tensile. So that's the TR, the conventional TR. Similarly, for compression, it is a factor of the unbraced length. So we should know the unbraced length of the member to assess its buckling resistance. And it's the reduction factor multiplied by the area and Fy, and then there's this factor which is related to the buckling. Lambda, which is KL over R, multiplied by a square root of Fy divided by pi 2e. Hopefully you have gone through this in the steel design course to assess the compression resistance of a member. However, normally we just jump into the manual of a steel construction and it tells us the capacity, the compression capacity. You see like this page that is open here, or I've taken probably a photo, is the factored axial compression resistance CR for different types of members, different types of HSS. So with mass and different thicknesses probably of the member. And this is the different lengths, because this is very length. This buckling resistance, in a way, compression resistance is length dependent. And for different lengths, the code provides the capacity. The longer the length, the lower the capacity. So basically this equation compressed or elaborated into a table. Now, next step for steel design, we went through the steps. For steel design, it's necessary to assess the, hold on a second. Okay. Yeah, I should finish in 5 minutes, which is fine. So we should assess the probable brace resistance for the purpose of evaluating forces on connections and other members upon yielding and buckling of the bracing members in capacity design. The probable tensile resistance of bracing members, T probable, the probable compressive resistance at first buckling, C probable, and the probable post-buckling compressive resistance of bracing members, C prime probable, shall be taken as tension probable. Is almost the same concept as tension for design. The only change is that we increase Fy to Ry multiplied by Fy. So we use an increased value of yielding. Similarly, for compression probable, we use the same as tension probable, but not greater than certain value, not greater than half of the, 1.2 times compression design, not including phi. So divided by phi and then increase by 1.2. It's as if your Ry is 1.2, where CR is computed using Ry, Fy, and RSH equal to 1. RSH, I barely use it, so it looks like it's always 1. So just ignore RSH. We are mostly discussing Ry multiplied by Fy. That's an important factor for us. And C prime, like post-buckling capacity, is 20% of the tension capacity, but not greater than, limited to CR over phi, similar to the above like equation. Each of the two loading conditions, the compression acting braces attaining their probable compressive resistance at first buckling, and the compression acting braces attaining the probable post-buckling compression resistance. So we check for both of them, for post-buckling resistance of compressive members and for probable compressive resistance. So both these two loading conditions shall be considered as occurring in conjunction with tension acting braces developing their probable tensile resistance. Probable bracing resistances. Capacity designed for steel requires the use of probable brace resistances. The probable tension, AGRY-FY, as we showed in the previous page. Compression, probable compression resistance is the minimum of the two. It doesn't need to be larger than the tension. However, say similar to other cases in capacity protection, we don't use phi factor and we increase the steel capacity, steel yielding capacity. And the post-buckling capacity is limited by 20% of tension capacity, but doesn't need to be greater than this value, like not using phi to calculate the compressive capacity of the members. Yeah, I think we did a good job. We will go through one example to establish this. It still looks weird to me, but it does the magic. It's magical. It's a good solution. And when you get used to it, when you completely comprehend it, then you will see that the intention is to create good seismic force resisting steel structures. Now you can ask your questions before the end of the class, and I can stop sharing the screen and I will talk to you guys on Friday. And please submit all your reports by midnight today. This is the final one, so there won't be more changes. Just add as much stuff as you like. And I think we previously said that not more than 30 to 40 pages. So put the additional stuff in the appendices. Thanks a lot. I will see you on, or you guys mostly see me on Friday, and I will talk to you on Friday. Take care.